Hi CalKV, this is a video on the law of exponential change. Write a differential equation for the statement. The rate of change of y with respect to x is proportional to the difference between y and 4. So the first part, the rate of change of y with respect to x, that just translates into the derivative. So we have dy dx is, and now we have this phrase proportional to the difference between y and 4. So proportional means that it's not exactly equal to the difference between y and 4, but it's just off by a factor. And so we often say that the factor is k. I suppose it doesn't have to be k, but in our class we just tend to do that. So k just represents that constant of proportionality. Letter B, the rate of change of a with respect to m. So we have dA dm is proportional to the square of m. Letter C, the rate of change of q with respect to t, so that's dq dt, is inversely proportional to the cube root of q. So this word inversely is different than we saw in the previous two problems. And so there is still a constant of proportionality, but the cube root needs to go into the denominator. The reason that it goes into the denominator is because when this amount gets big, it's actually making this amount over here small, or vice versa. So if this amount gets really small, then this one's going big, and that's an inverse understanding, versus over here when one side goes up, the other side goes up. So we tend to say that these two are directly proportional. And letter C is an example of an inverse proportion. Letter D, a new cereal product is introduced through an advertising campaign to a population of 1 million potential customers. The rate at which the population hears about the product is assumed to be proportional to the number of people who are not yet aware of the product. So the rate at which they hear, so that is dHdt, and yes, you can introduce some variables there, is proportional, so there's the direct proportional again because we don't see the word inverse. And it's the people that have not been made aware. So if H represents the people that have been made aware, because that's kind of how we clarified the first part, the rate at which the population hears, that is H, then this amount is the 1 million people minus the number of people that have heard it, and that number right there represents the people who have not heard. All right, so the reason I did all of that is because there are times on the AP test when like a multiple choice would come up and they would want you to write a differential equation for, a sentence. And another reason is because of this idea here. The rate of change of y with respect to y is proportional to y. And in math terms, that translates into dy dt is equal to k times y. And I'm going to take you through a solution for this, so finding out what the equation for y is, to show you some connections to other classes. So we do our separable variables. So dy over y is equal to k dt. We integrate both sides. So the left is the natural log of y is equal to k times t plus c. And now if I'm trying to get to y, I raise my right-hand side to so it becomes the exponent on e. And we remember our rules with exponent properties that if you're adding an exponents, you're actually multiplying numbers here together. And then we just end up writing it as a big C. So like this is just a number, and we simplify that to be just big C. And even further, your book tends to replace that big C with yo. So what we end up seeing here is that the differential equation dy dt equals k times y. always, always, always translates into the exponential function. And you guys have been working with the exponential function for a really long time, since Algebra 1. And I know you did it in Algebra 2 when you talk about growth and decay. And so this tends to be a reason why it's brought up in calculus, because now you have an understanding of where the exponential function comes from, that you guys can actually separate the variables and derive where that equation comes from. So now let's talk through just some concrete examples of this. So if you have dy dx is equal to 7 times y, you can immediately go to the equation. It's a recognition thing, that if you understand this to have come from an exponential function, then you can just write the function right away. So we know it's going to be e to the kt, and that right there is your k value. So it'll be to the 7t. And the next thing to figure out is this coefficient. So when we plug in 0 for x, e to the 7 times 0 is just going to be e to the 0, which is 1. So we know that the output has to be 3 for sure. So 1 times 3 gives you 3. Therefore, in all of these problems, you can very quickly build that exponential function. The next example, dp dt equals 0.6p with p of 0 equals 8. That immediately transforms into the exponential function y equals 8 e to the 0.6 t. Sorry, go back to the other problem. That should be an x. What I'm trying to do is be consistent with my variables. So this is x because that's x. This is t because that's t. And the next equation immediately writes as an exponential function 17e to the negative 1/2 m. An experimental population of fruit flies increases according to the law of exponential change. So this law is that differential equation connection, that we can use an exponential function for this situation. And it's the first time that we're using this law phrase to determine that. So there were 100 flies after the second day and 300 flies after the fourth day. And we know that yo-ect is the equation that will work with this situation. So here there's like no calculus that we're seeing, it's just this connection with the law of exponential change that we know we can work with this equation. So I'm going to start plugging in some numbers. We've got 100 equals yo e to the k times 2. We have 300 equals yo e to the k times 4. And so you're missing two different variables here, and so this turns into a system. Yo is going to be equal to 100 over e to the 2k. And now we're going to make a substitution. 300 equals 100 over e to the 2k times e to the 4k. Now you know exponent properties say that you can subtract exponents, so 4k minus 2k is 2k. E to the 2k is equal to 3. Go with logarithms here, so we have the natural log of 3 is equal to 2k. K is equal to the natural log of 3 divided by 2. Keep in mind what the question is asking, and it's asking us for how many flies are in the original population. So we just found the k value, and now the next or the last thing to do to answer the question is to figure out yo, because that represents the original population. When time is 0, yo is that initial amount. So yo is equal to 100 over e to the 2k. And k is natural log of 3 divided by 2. So working through the math here, we have 100 over e to the natural log of 3, which is the same thing as 100 over 3. So it sort of doesn't make sense in a context because that's going to end up being a decimal, but it's pretty good. I mean, we're trying to model real life situations with continuous functions, and so it doesn't always work out perfectly. But that's pretty close. So that's the initial amount. So just as a recap, the reason that this topic comes up in our calculus class is because of this right here, that you can finally understand where the exponential function comes from, that it represents a differential equation, that the rate of change of y with respect to t is proportional to y. And those variables can change based on what we're talking about, but in a basic context, you can take your differential equation, go through your separable variable process, and understand that every differential equation that's of this form can be immediately written as an exponential function.